Done.
Hello, good morning for some of you. Good afternoon. I am Ana Flávia Nogueira, the director of the Center for Innovation on New Energies, Cine. Cine was established in 2018. Cine is a center is sponsored by São Paulo Science Foundation Research and also for Shell. So at the moment we have 200 researchers working at our center. Continue the series of webinars, Cine webinars. It's my pleasure to have here as a speaker today, Professor Aron Walsh from Imperial College, UK. Professor Aron Walsh is a collaborator of one of our 4 programs, the Computer and Material Science Division, that is coordinated by Professor Juarez Silva, located at University of São Paulo in São Carlos. So I invite Professor Juarez at our studio to introduce Professor Aron Walsh. Juarez?
Okay, Ana, thanks very much for the introduction. Okay, for the few words, nothing more about Cine. It is a pleasure for us to be here. Okay, as Ana mentioned, my name is Juarez da Silva, and the coordinator of the Computational Material Science Division. It's my pleasure here to introduce Aron Walsh, because I know him for quite a long time. We met the first time with Aron was beginning of 2007, in the National Hildebrand Laboratory. He was, now he's young, but that time he was even younger, okay? Because that time he was, so I thought for us, a new postdoc is coming, he looks young, okay? When you saw him, we really saw that he was young. And then Aron, he got his PhD, awarded PhD from the Trinity College Dublin, Ireland. And for what I remember, he was one of the youngest to receive a prize, but he was one of the youngest PhD to got the PhD of that year in the full Ireland. So it was a very nice prize for him. It shows that that time he was really doing very well in science since his career was started that time. Then I have a pleasure, we shared the same cube for almost 2 years and a half, and we have published several papers together. Start with indium oxide story, when you make a very nice contribution. A nice talk that emerged, a very nice paper, a very nice contribution, well recognized by the community. And then I left NREL, the National Independent Laboratory, first, I think it was in the July 2009. He stayed there a few months later. And then he went back to England with a Marie Curie fellowship. And then he stayed, I think, in London. And after that, he moved to the University of Bath. However, as his career went very fast, and then to the sky really fast, then he came back to Imperial College as a full professor, and then as a leader in the area of perovskites, based on the last 10 years, he's worked on that field and provide very great contributions alongside with the several experimental groups in the world. And then, because of that, in the last 5 years, he received several prizes recognizing his contribution in computational material science, contributing to the field of the perovskites. Okay, few of those prizes can mention the European Ford Prize that really recognizes his contribution to material science. Okay, Aron is not just a great researcher; he's also a friend too. Okay, we have as you say, I don't forget that moment. It was me, Aron, Rondin, and on the house of highway there in Colorado. And so I say, here I could manage to have a team strong like you, but you three form a very great team together, and Aron really make along of us make a star, okay? Because I'm here in São Paulo, Rondin is in China, and also Aron is in Imperial College. It's really great to see a friend become very successful like that. And this can be realized by the recognition of the number of citations above 30,000. The int factor is nearly 100 in the Google Scholar, okay, and soon we're going to go above that. We've put himself among the top researchers in the world in computational material science. Okay, I'm not ashamed to say that, because a nice friend that I have collaborated for several years and then keep in contact with. Today, now he's going to talk for us here today. He's going to revise several of his achievements in the last years. Aron, it's a very great pleasure to have you here, and also to keep this contact further on. And we expect that all centers can build up a strong and further collaboration for the future. Okay? Thanks a lot for you to have you here. Now I just provide the word for here, and I have many people is willing to listen to recent achievements.
Thank you, Juarez, for the very kind introduction, and really great memories from the time that we worked together. So I'm going to kick off now. So hopefully my screen is sharing. So today's webinar is about computer-accelerated materials design. And I guess, first of all, thanks to Anna and Juarez for the invitation to speak. And thank you all for joining. And I hope you're all staying safe and productive these days. It definitely hasn't been the year that we expected it would be. So as Juarez introduced, so originally I'm actually from Ireland, and I studied chemistry at Trinity College at Dublin. And it's a university actually most famous for its graduates in literature. So including, for example, the author Bram Stoker, who wrote Dracula while in Dublin, but also for scientists. So William Hamilton is a graduate from Trinity, who of course developed Hamiltonian mechanics, which will come up later in my talk. So now I'm based at Imperial College London, so in South Kensington, in the Royal School of Mines. So the Department of Materials occupies space in that building. So this is an old picture of the building, and my office is down towards the end. Unfortunately, I haven't been able to visit since March, so I've been working from home, I guess, for the past 6 months. And one of the, I guess, motivating factors for me to move to Imperial was to join the Thomas Young Center. So this is a special center for the theory and simulation of materials. It connects researchers across London working on that topic. So over 100 research groups. So it gives us a real critical mass for, I guess, knowledge and expertise in theory and simulation. So we have joint seminars, workshops, and training for students on the topic of theory and simulation. So my group is focused, I would say, generally on modeling excitations of crystalline materials. So looking at electronic excitations, so redox processes, looking at vibrations, so phonons and crystals, and looking at optical excitations, so in particular related to solar cells and defects, and increasingly looking at exploring new chemical spaces. So I guess what used to be seen as high throughput computational chemistry, now sort of moving into the field of machine learning. So what I want to do today is sort of give it a gentle introduction to my field and get across some of the exciting changes that have been happening. But first, so just a couple of slides, I guess to emphasize some of the things that Juarez was saying on my collaborations with Brazil. And I guess my first introduction to Brazilian science was really sitting beside Juarez. So here's a photograph from back in 2008. So I was at Juarez's house for the birthday of his son, Patrick, who I guess is far beyond 4 years old these days. But really, I had a wonderful couple of years working with Juarez, where we shared the same cubicle at the National Renewable Energy Laboratory. So situated in this building, the SURF. You can sort of see there's not too much going on around the area, so that you're surrounded by mountains. So we had a lot of time to focus on research and collaboration. So it was an incredibly productive time, so working at NREL. And one of the main topics for our collaboration was transparent conducting oxides. So these are sort of essential components of solar cells, so materials that are transparent to sunlight, but allow you to collect current. And so one of our first, I guess, collaborations that's been one of the most successful was on indium oxide and understanding differences between electronic and optical processes. But generally, we had a series of really nice work looking at different materials, indium oxide, gallium oxide, aluminum oxide, and various solid solutions. So I really look back fondly at my time at NREL and also working with Juarez. But then a few years later, actually, I hosted another Brazilian researcher in my group, so Clovis, who joined for 1 year, and he came as an expert on alloys. So he'd spent a long time working on semiconductor alloys for his PhD, And he came over to Bath, and we spent quite a bit of time focusing on complex perovskite mixtures. So mixing different types of perovskites to form quaternary solid solutions. So it's a very difficult problem theoretically, and he brought some really useful insights. And he was also there at the right time when mixed anion perovskites started to become popular, so for halide perovskites. So he helped one of my students, Federico, develop some tools for looking at the distribution of iodine and bromine in some of the methylammonium lead-based compounds. So far, I've had a really productive series of collaborations with Brazilian researchers. But that won't be my focus for today. So I guess the motivation for what I'm going to speak about today is the timeline associated with developing new energy technologies. So if you look in the past, typically it takes a couple of decades to go from discovering a material to actually realizing a commercial device. And there've been a number of nice studies reporting how modeling and computer simulations can help accelerate this process. And it can accelerate at different stages in terms of identifying materials initially, and optimizing the synthesis and fabrication, to actually accelerating the diagnostics of devices. And the predictions are that we could decrease the technology timeline by a factor of 10. So using the latest tools in simulations and statistics, we should be able to go from 20 years to developing new technology to 1 or 2 years. And this is incredibly important when we're looking at the climate crisis and developing the technologies that we need to achieve, for example, net zero carbon emissions. But what I'm really going to focus on today is on the material selection and optimization part of this cycle. And so a big driver for this would be the concept of materials design. So the dream, what we want to do is be able to run a computer simulation where the input to the simulation is the property we want, or combination of properties or metric. We run a simulation, and the output that we get is the chemical composition and the crystal structure that best give that property or metric. So this could be, for example, solar cells. So we want to identify a new active absorber layer. We know what combination of properties we want, from absorption of light to generation of current. And then we identify the structure that can yield that property. Okay, so that brings me to sort of the outline. And there are two sort of relatively concise parts for this webinar. So one focused on, I guess, the present activities in materials modeling. So how we simulate ions and electrons in crystals. And then the second half, I'll focus on some of the more recent developments. So looking at the power of data and statistics. So for a lot of this webinar, I'm really taking a step back from my active research to try to give you a flavor of some of the developments in the field. Okay. So the starting point, so I was trained as a computational chemist. And just to give you sort of the current formal definition of what that is. So it's using mathematical methods for the calculation of chemical properties or for the simulation of molecular materials behavior. But it also includes synthesis planning, database searching, and combinatorial library manipulation. So it's quite a wide sort of perspective on what computational chemistry is. So it's not simply just using Gaussian to calculate the optical properties of a particular molecule. It's really evolving into something a lot broader, and something that many chemists, whether you define yourself as a theorist or an experimentalist, are going to be using some form of computational chemistry in their research. And of course, it's a discipline that's been evolving quite rapidly. So if you look back in the 1950s, I really like this photograph of, this was a state-of-the-art 5 megabyte hard drive developed by IBM. And you can see it being uploaded sort of onto a truck, so by 3 or 4 men. And interesting thing now, obviously, memory storage has miniaturized, but with similar dimensions this year, we've seen the first commercial quantum computer. So the IBM Q system with very similar dimensions. And you can really see an exponential growth in the power of quantum computing So where is that going to be over the next 50 years? And is that going to help us do new and exciting things in computational chemistry? So that's one really big question right now. So the starting point for, I guess, modeling chemical systems is molecular mechanics. So thinking about the application of classical mechanics, so Newton's laws, to model chemical systems. So often this is using analytic functions that describe sort of the stretching or bending that occurs in molecules or in crystals. But probably the first course you take on, I guess, bonding in chemical systems will cover the Lennard-Jones potential. So this is sort of one of the first milestones in computational chemistry. So what John Lennard-Jones was doing was thinking about the interaction of a noble gas with the surface of a solid. So you have a gas, well, you have a surface, you have a gas. So far away, there's no interaction. But as you bring the gas closer and closer and closer, you start to get some favorable interaction, but bring it too close and it becomes repulsive. And that's what this type of potential energy surface describes. And you can describe this with sort of this 612 polynomial. And so there's some branches of physics where people will study the properties of Lennard-Jones systems for a whole career. But if you're interested in, I guess, materials and complex molecules, it's not really useful itself. So a wide range of functional forms have been developed for describing the structures and properties of, I guess, real molecules and materials. So there's some very specific ones. So you have a range of 2-body, 3-body, 4-body potentials. And the challenge when you go to sort of these higher order potentials, you have more parameters to fit. So then you need more training data in order to develop a reliable model. So that's one of the limitations. But the big advantage of these types of simulations is that the functions are very easy to sum, they're very easy to multiply, to integrate, so you can perform very large-scale simulations. So some of the state-of-the-art in this field would be simulating more than 1 billion atoms. So you've seen examples sort of applied to protein folding, finding vaccines for COVID, radiation damage in crystals. And this is just one recent example from the literature which I really like. So it's taking a large simulation cell of liquid iron, cooling it quite slowly, and what you see is the emergence of microstructure. And so this is using quite a simple interatomic potential. That microstructure wasn't included in the original model, but it's something that emerges due to the collective interactions between the atoms in the system. So without worrying about it, you actually get the emergence of grains and grain boundaries and dislocations. And it just shows you how quite simple models of interatomic interactions can give you quite complex materials behavior. Okay, but generally, I'm more interested in electrons and electronic processes. So you have to move away from classical mechanics to consider quantum mechanics. And generally here, what we're dealing with is numerical solutions of the Schrödinger, or if you're dealing with heavy elements, the relativistic Dirac equations that describe electronic distributions. So these are necessary, for example, if you're interested in batteries, where you have redox processes, you're adding and removing electrons to a system. So yeah, we're dealing with these sort of partial differential equations. We have a Hamiltonian that describes the energy of the system, which is usually broken up into kinetic and potential energy terms. And in these sort of simplified forms, the equations can seem quite simple, but of course, due to the many-body problem, they become impossible to solve exactly when you have more than one electron and proton present. So we need to make approximations. And in material science, the most common approximation or reformulation of quantum mechanics is density functional theory. So realizing that this many-body picture is quite complex, just writing down all the terms for each of the individual electron-electron and electron-ion interactions becomes quite messy. Even the largest computers in the world have difficulty solving them. So in DFT, what we do is actually forget about all of these individual interactions and just think about a real space effective electron density. So it really simplifies the problem from this multidimensional wave function to a real space electron density. Of course, in practice, there are a few subtleties, but this has really become the most actively used tool for modeling the properties of materials based on quantum mechanics. And of course, Walter Cohn has to be credited with developing a number of the initial theorems that were used in DFT. So I see two big problems with DFT. So one is a computational bottleneck. So the underlying algorithm scale as order n cubed. So that means if you want to deal with a system that has 10 times more atoms, it's going to cost you 1,000 times more computing processing time. So this sort of introduces a bottleneck in terms of the complexity of the systems that we can model. So most DFT calculations are in relatively simple unit cells, sometimes surfaces, but we're quite far away from actually simulating realistic microstructure. So even using the latest algorithms that are available. Second problem can be recovering chemical concepts. So I guess in chemistry, physics, and material science, we're used to, I guess, quite straightforward concepts like covalent bonding, ionic bonding, oxidation state. It can be quite difficult to transform from either a many-body wave function or a delocalized electron density to the concepts that we're quite comfortable with. And there can be many points of confusions along the way in terms of what types of bonding is happening in a particular system. And you have to be very careful on how you decompose the electrons in our distributed system into atomic species or molecular species. And that's just one point of contention. Well, at least I've been involved in a couple of debates over the years. But the big plus side for DFT-based modeling is that there's been a big shift over the past decade towards open source packages. So trying to lower the barrier to entry. So you no longer have to have a lot of money to run these DFT calculations, apart from the computers. And there's a range of packages like Abinit, CP2K, GPaw, where you can go to the websites, you can download the code, you can install it on your laptop, and you can run some quite simple DFT calculations. You just need larger computers if you're going to be running sort of larger, more sophisticated simulations. But as well for, I guess, the pre-processing, sort of setting up structures, and post-processing, sort of trying to generate pretty pictures and different types of analysis, again, there's a range of packages appearing. And ASE is one that's very attractive. So based in Python, open source, you can download it, use it. You can also modify and contribute to it. And this is a really nice way for students to start their first sort of materials modeling. So it's a very, compared to when I started doing work in this field, where a lot of it was just looking at a blank terminal, doing a bit of maths to figure out lattice vectors and angles. This makes it a lot more interesting and fun to start. But I'm guessing a lot of people watching this webinar are not modelers, and you might be asking, actually, well, what is materials modeling going to do for me? Or how can I compare it to my experiments? And this is something that's been improving over time. I think the gap between theory and measurement has been decreasing. And I would say there's several classes of things that we can calculate. So it can be structure. We can do structure prediction. We can think about vibrations and compare to infrared and Raman. And we can think about thermodynamics, so compared to calorimetry measurements, for example. And increasingly point and extended defects. So we can predict what defects should be present, how they might diffuse in a material, and compare, for example, to impedance spectroscopy, to tomography, and to a range of different microscopic probes in crystals. And we're seeing many examples in the literature of how well, I guess, modeling and measurement can match when comparable sort of experiments are performed. So I'll just give two examples of, I guess, some of the research in my group that's using some of these more conventional methods. So we have a big active project in the UK called the Faraday Institution, related to battery research. And some of our work is understanding thermal processes, which can be related to degradation, but also related to some performance issues. So using some tools looking at phonon frequencies and phonon lifetimes, we can predict thermal transport across some quite complex solid solutions. So looking at mixtures of lithium, cobalt, manganese, and nickel oxide, and how the vibrations change, but also how the difference in heat retention changes through that phase diagram. So those types of simulations just wouldn't have been possible 10 years ago because of the expense involved in computing these phonon-phonon interactions. So the other thing we're spending a lot of time is trying to have more accurate models for solar cells. And I'm really interested in trying to understand the role of defects and how defects limit the performance of absorber materials. So we've been developing some methods. We have one package called carrier capture that enables us to go from defect concentrations, just saying defects exist, to how they actually interact with electrons and holes in solar cells. And so it brings us, we have a workflow like this. It's a little bit, I guess, messy at the moment. So we sort of have two strands. We think about the perfect crystal that determines radiative processes, and we think about the imperfect crystal. So what defects are present, what's the capture coefficient of each defect. We sum them up to give a non-radiative rate. Then we can combine non-radiative and radiative to come up with a metric that we refer to as trap limited conversion efficiency. So trying to come up with something that's a little bit more realistic than just the Shockley-Queisser limit. So Shockley-Queisser limit just tells you because you have a certain band gap, you should be able to reach a particular level of performance. So with this material CZTS, Shockley-Queisser will tell you the material should be able to perform at 32%, so light to electricity conversion. But if we look over all growth conditions at the defects that will form, we can predict using this metric that the best performing CZTS solar cell should have an intrinsic limit of about 21%. So there's about a 10% loss just due to the fact that certain defects are unavoidable in the crystals. So we believe this metric can be quite useful for screening new systems, at least just to tell you initially, should they be useful to, I guess, spend more experimental time in trying to optimize the absorber and the devices? Or is there some intrinsic bottleneck that the material, maybe you can't get over 10% in some cases? So we've had just our first sort of showcase application. This is something we're further developing at the moment. Okay, so that brings me to the end of the present. So thinking about interacting ions and electrons. So what I'm going to move on to next is thinking about data and statistics. So there've been a number of suggestions, and I guess it's going to be impossible to ignore I guess the narrative that's appearing in the literature, but we're entering a new era of data-driven science. So this is one particular illustration of, I guess, evolutions in the scientific process. So maybe the foundation of science is reproducible experiments. So that's the first paradigm. Then we had the advent of model-based theoretical science. So the era of electromagnetism, of thermodynamics, and even of quantum mechanics at the start of the 20th century. Then over the past few decades, we've had bigger computers, and we can solve more complex models and make, I guess, more sophisticated predictions. But that's, I guess, based on the analytic models and numerical solutions and numerical integrations that I was talking about earlier. And the suggestion is now in the 21st century, we have a new range of tools related to artificial intelligence and machine learning that's enabling sort of big data-driven science. And so that's what I want to discuss in the second part of this webinar. So the main topic would be machine learning. So machine learning combined with chemistry. And just, I guess, my most simple definition of machine learning, it's statistical algorithms that learn from training data and can build a model to make predictions. It's most appropriate where standard models fail. So if there's a problem that you can solve using existing methods, you're probably better off using them. Machine learning is best for models that are perhaps too complex to be solved using conventional methods. And they are approximate. So you're sampling, you're building an approximate model that's only as good as the data that you provided. One of the challenges as researchers is that it involves many different concepts. So related to programming and algorithms, to thinking about the relevant features for your system, but also data. So are you getting your data from simulations? Are you getting your data from measurements? So there's many things to consider. And this is really a field that's still it's still formulating. It's in rapid development. But if you look into literature, there's many different applications appearing. So directly related to computational chemistry. So people developing faster or better computational tools. So developing more universal interatomic potentials, or for example, some methods for many-body systems that were too expensive to solve using existing methods. Trying to derive new knowledge from existing data. So for example, data mining from the literature, so natural language processing, extracting synthesis recipes from what's been published already, and can we learn from that? And a lot of exciting research on self-driving research workflows. So if you have a system where you can computer control the synthesis and characterization, you can have a closed loop system where you're depositing, characterizing, and then optimizing all in a consistent workflow. So you can generate your own data on the fly. So many exciting developments. So within machine learning, there's a few different strands or classes. So you can think about regression. And of course, many physical chemists do this by standard. You have data, you fit particular functions as best you can. You can think about classification. So you have a large data set and you want to break it up into distinct categories. So maybe you want to predict the reaction outcome. So if you set up precursors and what is going to be the outcome in terms of the reaction. And you can think about clustering. So you've maybe a lot of data of different forms and you want to group it in a certain way. This has been used a lot recently in tomography and microscopy as a way to identify particular regions in your data set. And there's areas such as reinforcement learning and adversarial networks as a way to sort of optimize your system. So maybe you want to develop a new molecule with a certain property or a new crystal with a certain property. This would be a way to bias your system towards identifying such a compound. So there's many flavors of machine learning approaches. If you're very interested, actually, some of my colleagues, so Sam Cooper and David Dye and others, developed an online course in MOOC for the underlying maths of machine learning. So it's not really on the applied end of sort of predicting the properties of materials, but if you want to understand how some of the algorithms actually work underneath, and this is a really fun course to join and learn about that. Okay, so I guess my word of warning is that not everybody is on the machine learning sort of train. And you hear a lot of healthy skepticism about machine learning. And I really like this cartoon. So it's showing, okay, this is your machine learning system. So you pour data in one end. There's a lot of linear algebra, and then you get answers at the other end. And if something goes wrong, you just have to sort of tweak your algebra a little bit. And this is, I guess, a common perception or criticism of machine learning as being sort of a black box approach. You're fitting data, but where's the science or where's the physics? But of course, researchers in this field are well aware of those issues. And there's a number of very active developments. So on one side, uncertainty quantification, so trying to understand the limits of predictions and trying to put error bars on predictions from machine learning models. So that's a really exciting avenue. So trying to come up with more interpretable models. So instead of just having a black box system, trying to understand what's going on behind the hood. So what features are important? How are they related? And can we really learn something about the model that's been trained? There's another branch on physics-based models. So trying to combine some of the physics that we know. So we have some really good general equations. Can we combine them with data? So it could be in terms of parameterizing the equations. It could be trying to generalize the equations to regions of space that they're not very comfortable, so high pressure, high temperature. But instead of just having a purist sort of generic machine learning model, trying to incorporate some of the physics directly to make the models more powerful. And then one other important area that's very important for material science, because our data sets are often quite small, is transfer learning. So if you learn about one system or one property, can we transfer that model to learn about other properties? So these are the type of things that people are thinking about, and it's a really active area of development with many papers appearing each week on these topics. Okay. So even if you're not interested directly in machine learning, a big advantage of these developments is that there's a lot of new tools that enable us to enhance our research. So in the way that we deal with data, so of course Python now is very widely used. We're teaching it to our undergraduates from first year. Packages like Pandas for dealing with data structures, Jupyter notebooks for documenting how you process data. And then in terms of modeling, maybe SciPy for just sort of standard linear algebra. A wide range of packages for conventional machine learning, for deep learning, and really nice tools for visualizing multidimensional data sets. So matplotlib, quite conventional, but Bokeh and Plotly for sort of interactive plotting and making very funky supplementary information. So there's a lot of exciting things happening in the field. So I think the days of just using, I guess, Excel and Origin and MATLAB are really limited. So I think we really don't need all of those commercial codes. I think there's a lot of these packages you can download, you can contribute to quite freely. So just one applied example. So working in, I guess, condensed matter physics or materials chemistry or materials science, you spend a lot of time learning about crystal symmetry and space groups and reading the crystallographic tables. But these days you can download SPGlib, a really nice Python library. And this really accelerates symmetry analysis of crystals. Of course, there's other tools available, but I think it just changes how you work and deal with, I guess, complex materials. So when I started my PhD, I spent a lot of time thinking about symmetry, understanding Wyckoff positions and how you rotate things. And these days, just as much effort, I guess you're spending more effort on the programming side and understanding these libraries, and that really accelerates workflows. So suddenly you can analyze the symmetry of 1,000 crystals instead of just doing one at a time. Okay. A second big movement relates to open data. And this is really something that is needed to support the development of data-driven science. So making data available at the time of publication often, but could be at the time of sort of submitting a PhD thesis. And the things that we have to consider are, I guess, reproducibility. So making data available so, I guess, other groups can reproduce what you're reporting. So this could be in experiments making raw infrared or NMR spectra available. Reuse, so this also enables new types of studies. So if I want to look at trends in a particular UV vis feature of a material, well, wouldn't it be great if I could go to a database and download everybody's UV vis spectrum and then perform consistent analysis? And the third then is feeding into model development. So the power of machine learning that I mentioned really depends on the quantity, the quality, and diversity of the training data that you have available. And the majority of studies so far are really limited by data. So we need to be better as a community in making our data openly available as much as possible. And there's a number of international, I guess, activities, guidelines being developed to encourage us and show us how to make our data available more effectively. And of course, crystallographers really had a lead in data sharing. So they developed the standard CIF format, so crystallographic information file, which is both human readable and machine readable. So you can open up a file in a text editor and you can understand it, but you can also have a parser that can read in 1 million CIF files. And 1 million is actually a number that's been reached in the Cambridge Structural Database, I think late last year. And that's quite an amazing story. So a database that was started in the 1960s. And then it became quite standard when you refine a crystal structure that you upload your structure file to that database. But wouldn't it be fantastic if such a scheme existed for properties as well as just structure? But there are a number of initiatives, I guess, ongoing initiatives for collecting data related to properties and related to energy, materials, and devices. So this is one project from Santa Barbara, and this was focused on, this one was thermoelectrics. So collecting data based on conductivity, Seebeck coefficient, element abundance, ZT metrics. So you can go to the website. So I think you can probably find from this DOI, but it's from the website of Ram Shashadri at UCSB. You can play around with what you want to plot and maybe identify your own correlations. And you can also click on each data point and it tells you both the material, but also the paper that data came from. So it's a really useful way for just, I guess, data mining, but driven through visualization. If you're interested more in batteries, of course, the US Materials Project is one of the most famous examples. But this is a project that's, I guess, populated by DFT-based calculations. So a really useful database where they performed high throughput calculations essentially on the whole inorganic crystal structure database, at least the materials that have well-defined atomic positions, and also some additional databases, perform DFT calculations of structures and properties. And the range of properties they've included is increasing over time. But they have a really nice battery explorer. So you can put in the elements you're interested in, and it will predict voltages, it'll predict capacities. So based on the DFT thermodynamics and also the structure, the composition, the density, and things like that. So it's a very useful screening tool. Even if it doesn't tell you the perfect material, it will tell you something about that chemical space that you want to explore. So how many known materials exist and how useful are they for that particular application? So that's a database populated by modeling. There's other databases populated by measurements. So this is one battery data set on the University of Utah website, and similar to the thermoelectric one a couple of slides ago, but you can plot different properties, so cycle behavior, sort of capacity retention, element abundance, and then you can look at the various trends. So this is really just people, I guess a lot of this is automated. No, I shouldn't say, it's manual. So people often, masters or early PhD students, will have gone through hundreds of papers and tabulated the information they contain. So looking at cycle behavior, looking at voltages. And again, this relates to open data, but so far, we're not very good at making such data available in a way that can be downloaded and parsed automatically. So natural language processing takes a lot of TLC to make it work for such complex property sets. So I'm very interested in photovoltaics. And I think so far there haven't been so many public data sets related to photovoltaic properties. But recently I've been involved in one project on emerging inorganic solar cells. So looking at materials that maybe wouldn't make it onto the mainstream performance tables. So they're not reaching 20% light to electricity conversion, but there's a lot of exciting research. So that progress should be documented and reported. So the first version was out last year. Yeah, I think last year. We've been working on version 2, And one of my roles is to do some better data analysis. So I want to make all of the data in the tables openly available. And we've been playing around with different plots, so looking at efficiency versus band gaps, and the performance of different systems compared to full Shockley-Queisser limit and 50% Shockley-Queisser limit. And then you can look, is the limitation in the voltage? Is it in the current? Is it in the fill factor? And you can then sort of see trends between different classes of material and maybe where the effort is required. Is it trying to reduce non-radiative recombination in the bulk? Is it possibly per device configurations that are being used? I think there are many developments trying to develop such data sets for energy technologies. But where I'm spending a lot of my time is using these sort of tools to explore new chemical spaces. So thinking about compositions, structures, stoichiometries, morphologies. So you've got a huge multidimensional space that's difficult to solve using conventional methods, but it's quite appropriate for using these statistical tools. Just to give one simple example, so we're not at the end yet, but one of my students, Kazuki Marita, was developing some models looking at the dielectric response of crystals. So if you could learn the dielectric response of known systems, how useful would those models be for looking at new materials? So that's one of the questions we wanted to answer. So we have a public data set of over 1,000 crystals, and we developed a few different models, so some based on support vector regression, some based on neural networks, and they both perform sort of reasonably well. But one of the nice things is we wanted to look beneath the hood at actually what are these models actually doing. So we're using something called SHAP analysis, which is something from that's been used in game theory before, to understand the contribution of each feature to the trained models. So understanding which properties are actually determining the dielectric predictions. And the really cool thing, what we could see, is that what was being used in the models are actually what we sort of know from conventional physics. So in terms of the importance of the density of a crystal and the importance of, I'm just trying to remember here, and the importance of band gap. And what we end up seeing is whether we're getting sort of linear or quadratic behavior, it looks very similar to some of the models that were developed in the 1970s, except of course there's a little bit more complexity in these models because we can be more general. So by having so many different features that each make small contributions, they help generalize the model. But what we see is that the biggest contributions are really from what we'd expect from standard solid-state physics. So that's giving us, I guess, a little bit of confidence in using such models for property prediction. Okay, so just, I guess, some additional advice. If you're spending more time than usual at home, maybe thinking about what you could do to make your research more effective, this was a really nice guide published in the ACS Chemistry magazine on 12 steps for, I guess, improving your data process associated with research. So thinking about data curation. So I think we've all been guilty, whether you do measurements or whether you do modeling, of you have all of your data present at the time when you're preparing figures and then you submit a paper. But after a few years, you forget exactly what data is where and what that label actually meant. So getting into a process where you have appropriate metadata, sort of to label where that data came from, some of the additional parameters that maybe are not explicitly listed in the files, that's the sort of thing that you can start to have a protocol for your lab sort of during this downtime. Okay, so that brings me to the end. So my conclusion is that many exciting developments in materials modeling, which I hope I've gotten some of them across today. And so what we're seeing is sort of analytical and numerical methods being enhanced with the addition of new statistical approaches. And generally, we're just limited by available data. And that's something that, as a community, we can improve going forward. So thanks to my research group, thanks to a collaboration network, which I haven't really gone into today, thanks to sponsors for the research, and thank you all for your attention today.
Okay, thank you very much, Aron, for the nice and very, right talk. You basically provide a very nice didactic talk for everyone that could follow up with. We had about during the talk from 130 to 150 participants, which is great. Okay, we have some few questions. Then I'll just make some questions here. First, I would like to start from general questions. Then we can go more deeper at some parts. I think that makes more sense. Okay. One of the first questions I say is for this question, I would like to see how do you see the future of quantum chemistry? Because there are several groups that are investing a lot of time and efforts in machine learning tools. We are building up a large database set, and several groups are doing in the direction of more or less close to the experimental, which are more or less work together, very tight to the experimentals, and they combine their forces together. And they are basically you are take advantage the fact that you have this result, which is very reliable, that can guide you how the simulation goes. And there's the machine learning too. And there's the different groups that are not, they are basically not on side, they're in the middle. How do you think that this will evolve for the future?
It's a really good question, Torres. And I think it's definitely a time of transition. And I think you're very right. So at the moment, you can see a range of different research. So you can see groups that traditionally would do atomistic and electronic structure modeling. They're starting to do some machine learning. And maybe I'm one example of that. Then you see new groups emerging that are specializing just in machine learning and statistical approaches. And then you see some experimental groups that have really nice automated setups, and then they're doing their own machine learning, sort of closed black box models. And I think all of that's sort of coexisting at the moment. But at least where I think the field is going, or where the most exciting research is going to be, will be with physics-based machine learning models. So combining some rigorous physical concepts with these statistical tools. So I think we still need to have the good training in our field, in condensed matter physics and in sort of solid state chemistry. But then we can use these new tools to help augment us. But I don't see, I think in terms of gold standard simulations, and I guess in machine learning, you say the ground truth. Quantum mechanical modeling, I think, is not going away because it gives us something very reliable, especially when we're looking at new systems or new concepts. But at least what I'm trying to do is get most of my group to have a little mix of doing atomistic and some statistical approaches. But it's quite challenging for students to master all of those concepts in the 3 or 4 years of a PhD. So I'd say not everybody can handle all of that. But I think going forward, to make you future-proof, I think just doing DFT calculations is sort of reaching a limit where we need to be more open and think about what we can model and how we can model it. So I'm not sure I answered your question. I don't think we haven't reached a steady state yet. I think there's many techniques sort of intermingling. So I think we just have to be quite open in terms of trying to use the best technique for a particular problem. But I think definitely computational chemistry and physics is changing now as a discipline.
Okay, that's good. Okay, I have more one question after that I will move to Ana Flávia, who has one additional question too. And then I'm going to take some questions of the participants too.
Okay.
You provide this carrier capture model when you try to really to estimate a better estimate for the performance of the solar cells. You show an example when you drop from 32 to about 21%. But this will be a general trend, or in some particular case of those type of materials, even the defects will play a larger role. While in some different cases, maybe the defect is there, but it's beneficial for the solar cells. Because in some cases, is the effect can be beneficial too, but in some cases can really damage the performance.
Exactly, and I think the case in point for that would be perovskite solar cells, where people know there are a lot of defects, but yet you can still get the very high performance. And so that's a case where I guess people are calling it defect tolerant. But your question, so I think for many of these emerging inorganic systems, so generally the solar cells suffer from having quite low voltages. And typically the voltages can be less than 50% of the bandgap. And that's a clear sign that non-radiative recombination is dominating in solar cells made from those materials. So it's generally believed that defects are really the dominant bottleneck for a lot of those technologies. And what we want to be able to do is to predict how much of a bottleneck. So maybe you have a material, so we don't have many test cases yet, but you might have a material where the defects are so deep and so abundant that the maximum efficiency might only be 10%. So then we could confidently say to an experimental group, maybe you should stop experiments in that system because it's very unlikely that it's going to make a viable solar cell. So at least that's what we're trying to work towards.
You basically want to use it as a screening approach to exclude, to eliminate possible candidates that based on the band gap could be a good candidate, but in fact it is not.
Exactly. Because I think in terms of quantitative, maybe we're not so confident to say 21% is the exact limit because there's a lot of approximations. But I think in terms of a general filter, I think it can be quite useful.
Okay, I got it. Okay, I just, Ana Flávia, want to put one question on.
Thank you for this very nice sparring talk. It's always a very pleasure for me to listen to you. So back to the defects in perovskites, because we are experimentalists. So about a question that I think my students, they might have to you, it's, you know that perovskites are very sensitive in the way that you make them. Depends on the temperature, depends on the methods that you deposit them, concentration of the precursors, solvents, atmosphere, whatever. So maybe you can, how the theory can help us, because I understand that you can predict the defects that we can find in that specific composition of perovskites. But at the end, this is not what we get in the lab when we make the devices, and sometimes we are surprised because we're expecting, like, let's say, suppose low voltage, but sometimes the voltage is higher than we're expecting from. So this is because depends on the way that you make them. This kind of solar cells, they're made by solution. I'd like to comment on that.
Yeah, that's a really good point. So one of the reasons I like metal sulfides and the chalcogenides is that often they're processed at quite high temperatures and in a sort of a thermodynamic limit. So often what we're assuming is an equilibrium population of defects. So you have some partial pressure of sulfur, you have a particular temperature, and then we can predict what defects should be present. For the halide perovskites, it's quite different because the materials are processed often from solution. You have precipitation reactions. And then you probably have many more kinetically driven defect populations compared to thermodynamically driven. So this means that we need to use slightly different methods. And some of them don't really exist yet for the solution processing to make accurate predictions on concentrations of defects in perovskites. And the additional complicating factor for perovskites is that the defects are also mobile. So then you have the ion diffusion on top of everything else, such as the carrier capture. And I think that gives rise then to a lot of the hysteresis behavior, and some of the large voltages, if you get sort of surface charging, can give you an interface dipole, for example. So I think perovskites are really interesting for a different reason, and mainly because they break a lot of the conventions of typical photovoltaic absorber materials. So it's a lot of work for theorists to do to develop more accurate models. And I guess as part of Cine, Juarez and other groups are working in that direction.
Okay, thanks for the question, for the answer. Now we have some additional questions for the participants. I have a question here from João Paulo Mendonça. He's a postdoc in my group. He's asking, do you think that these initiatives to publish the data of our works may impact the format of the scientific articles to make them more machine-friendly in the future?
I think definitely. I think that's a big issue. I think it will definitely increase the impact. So I think even at the moment, we were playing around with trying to do some natural language processing to extract some properties of crystals. But currently, with a lot of the tools, you're quite limited to open source papers. So papers that have been published in repositories on either institutional websites or in journals that are open source. And that already gives added value. It means I can access those papers very easily. But if you make your data transparent, I think definitely it's going to be used in more papers for machine learning papers. And it should definitely increase, if you're interested in citations, it should increase the citations in terms of that type of impact. But it will also increase the real impact in terms of people being able to use your data and models more effectively. So yeah, I fully agree with that point.
Okay, that's nice. There are some further questions here. For example, it comes from Juliano Bonassin. He's asking, first, congratulations for the talk, for the great presentation. Where and how the materials, basically the question is here, how the materials can be different from the machines itself, basically. And what are the challenges that humans you have in the machine learning approach? It's a more general question.
Yeah, so the philosophical.
Yes.
So I think there's I guess there's a split. So there's a number of experimental groups that are moving heavily towards automation. And so having more robotics in the lab. And some of them are quite advanced. So you can see robotics that can do simple sort of depositions and simple characterization. And so one of the questions is that replacing a PhD student? I think no, it's not. So the automation is doing something quite simple. It's mapping out some parameter space, but you still need to have the human in order to think about actually how to set up what space to map and also to perform the actual analysis. But it's definitely changing, even in the experimental context, in the skills that you need your students to have. So it's no longer just being able to use a pipette and deposit something. Even those students need to have some programming and some Python to do analysis. Okay, and then on the other side, I guess you have theorists who are working with these types of models. And I think, again, these are just tools that help you do something different, but they're not really replacing you. So for anybody that's done machine learning, 90% of the time is in processing the data and choosing the model. Actually training the model and applying it is really a very small sort of piece of the big picture. So most of it is human time, actually, I think currently in terms of running these models.
I think we have some interesting question now that comes from André Luiz Barbosa. You make a very good point that you could decide to tell this experimenter, okay, stop this material line with the class because maybe there's no future there for human defects. Then we have a question about that. If you make your decision to stop an experiment based on a calculation, you have to be really sure about its accuracy.
Yes.
What is beyond the FT for a computational material chemistry, for example? The accuracy of the FT, how should we improve it to make these decisions, to help it, really?
Yeah. And I think often, I guess there's a couple of different points. On one side, it's not always just DFT that's the limitation. It's the absence of temperature. So even if you had the perfect sort of Hamiltonian, some quantum Monte Carlo, if you don't have temperature, you're making a prediction that's essentially 0K, but even without the 0-point motion. So I think a lot of the exciting effort now is looking at finite temperature simulation, so including electron-phonon interactions, including thermal expansion. And I think that's an avenue where machine learning can help make the calculations more affordable, because electron-phonon interactions are very expensive to calculate. So I think we're moving towards a direction where phonon, I saw a question in the sort of comment list, someone was talking about phonons, and phonons are really good for developing more accurate interatomic potentials, but also for developing more accurate predictions. So I think for our gold standard, to be sure, as Doris says, if you want to be confident to say whether you should do the experiment or not, I think including temperature effects and then using the best electronic structure method you can. So maybe DFT. There's a number of nice papers with CCSD, with some quantum Monte Carlo aspect. They're becoming, I guess, more affordable for very small systems right now.
Okay, good. The question that you mentioned now about these funnels, there's one of the first questions that was put there about Alexandre Carvalho Dias, is the following: what's the best data that would be used today to train a force field calculation, a force field potential? Because with the machine learning open you, how to say, a Pandora box, concerned that there's several techniques that can be applied, but what would be the best data to train a force field?
Yes, and there have been quite a few papers on that topic even the last 6 months. So I think the typical procedure is to perform molecular dynamics simulations and then to use those trajectories as training data. But I think the counter argument is that MD only really samples a very small part of the potential energy space. So I think where things are going is having random sampling or random displacements. So you have some simulation cell, then you have random displacements of atoms, and you build up a training set that way. And there was one specific example from the group of Gabor Sassani from Cambridge on a machine learned potential for vibrations, I think in the past couple of months. And I think theirs was based on molecular dynamics, but they were developing a machine learned interatomic potential from that type of training set. But I think random sampling could be the way to go.
Okay, good. Okay, I have one question that comes from my side. Since that you mentioned a concern on the discussion. For example, nowadays, for example, the application of the dense material theory goes from the dense material applications for a class of materials, a statistical approach based on machine learning, and several analysis further. And as we know, because even also in England too, the time of the PhD is short. Okay, in my case, as I think for example, we are in the Institute of Chemistry too, when the skills on programming in Python, the student has some challenge to face. Okay, how do you think that? This is my question that can be very useful for the students that are following the talk. How do you think that is a good approach to deal with that problem and to have a group in which you have students with some expertise in machine learning and some students with expertise in dense theory, or try to train all of them and train both in both techniques?
It's a really good question. And I think generally, I don't think it really exists yet, but I think we need to have better structures in our graduate schools to help teach things in a more integrated way. But at least in my group, so a few years ago, what we started was like an evening informal session for people interested in machine learning. And then we used that to go through some of the basic techniques. And not everybody was using machine learning for their projects, but I think everybody now is interested. So if you think especially about future jobs beyond academia, having machine learning can mean a really big pay boost at the end. And in reality, it's for physicists, it's not very difficult. It's just some more statistics. But I think it's good for everybody to be aware, because I think there are so many papers in our field now based on machine learning. And if you don't have the core concepts, it's impossible to critically assess what people have done. So is it a good paper or a bad paper? Is it a useful model or not? And I think that comes to the training side. I think we all need to be aware at least of the basic concepts.
Yeah, I agree with you. You need to have some basic education on those tools, that if you need to use them to go in this direction, maybe you have at least the base train to start it. Yeah, I agree. In our chemistry course, we don't have basically the computational sciences a bit outside. In physics, no, I agree with you. The physics, they have a very strong background on that. Okay, now I have a question from the participants, from Christopher Handel. Here. Okay, I think you can see the question already there.
I'm just laughing. So Chris was one of my former PhD students.
Yeah, okay.
So, good question. So all of our data is biased. In part, we only report data that contributes to the paper's story. That's very true. I think we all have data sets that have never been published because it doesn't tell the story that we were trying to tell. So what do you think is most valuable? What to synthesize or how to synthesize it? I think both questions are valuable. In terms of what to synthesize, saying this material should be useful. But I think how to synthesize it is one, it's intellectually very stimulating. And I think there's a lot of nice work, obviously, machine learning, trying to learn from how people make current materials, and then how that can be adapted to predict how we can make this new material based on the similarity or substitutions. So I think there's definitely room for both. I guess just like there's room for synthetic chemists and I guess inorganic and physical chemists in terms of characterization. But I think that's a really good question.
Yeah, I think that is to say, because there's a point that we always just publish the data if you can build up the store. And many of the data we not publish it.
Yes.
Basically, machine learning tells us that maybe this data we should use it for something else.
Yeah.
That's a good one. Okay, I have some, say, when you mention about this natural language, for example, we have someone in our group also doing some effort aligning with that, try to start something, and then looking the published data, papers, and try to extract reliable and reasonable information based on the published papers already. If you can learn for something from what have been published already. It's not the data itself, but it's the story. Do you think that this research line inside of the material science, it could have help to combine with the machine learning, with extract new ideas from the crude data? Because one's analyze crude data, another one's analyze the interpreted data read, the story. How do you think these two things maybe combine, or do we have two independent approaches that maybe stay like that?
So I think I actually had a summer student looking at that problem. And it's natural language processing is incredibly difficult for scientific papers. And generally it's because of how we write papers. That, of course, we're often encouraged not to use the same phrasing twice. So there's a lot of creative words, but often we don't explicitly state everything that we've done. So we refer to previous papers, maybe we refer to supporting information. So what I was finding, at least, it takes a lot of human training to sort of classify each of the papers and each of the things you're looking for in order to get anything remotely reasonable out. And I think there's always an uncertainty over whether you're actually extracting the real data or not. So especially if you're building a very large data set. So there might be specific problems where the natural language processing can be useful, but at least in the cases we were looking at, we didn't manage to do anything very successful. And even in the big papers, there's a big paper, Nature, from the group of Gerd Cedar last year, and that was based on processing 1 million papers, I think. But when you look carefully, it's based on processing 1 million abstracts, because an abstract is just a single block of text. Actually parsing the full papers themselves is a lot more difficult. So maybe there'll be some breakthroughs. There are probably some nice packages out there. But I think just in terms of how we write and report our data in the past, it's very difficult to learn from that directly.
We have some additional questions here from participants. That are more technical ones from José Carlos Germino. Okay. Please, thank you very much for the nice talk, Aron, for the exciting talk. This is I have one question. Does the use of plane waves, base set functions to describe lead or highlight perovskite materials is adequate, or atomic-based functions? It's a more technical one.
Yeah, very technical. So I haven't found any issues. So often in our group, we use a combination of plane waves, so VASP often, and FHI AIMS, which is an atomic sort of numerical orbital basis set. And we've calculated the halide perovskites in both. And once the basis sets are converged, you get pretty much identical results. So I don't think there's any special issues. So maybe if you go to F electron systems, that's in the past where plane waves have had some issues. And so moving to like LMTO based methods and things like that. But for these closed shell systems, I don't think there's any major issue with plane waves.
Okay, I think that's good. Okay, I was happy to listen to the answer for the codes, because I saw when you talk on the list of open source codes, I was thinking that you give up the VASP code, the FHIMs, everything else. Okay, that's good. Okay, I think Ana Flávia want to say a few words now, because I think we have several questions further, and then I think that several questions here are more or less, they are similar to the one that you answered already. I think it's already very nice. We already extend our time for the question, basically for the half of the talk already. I think I will give the word now for Ana Flávia, if she can make a final question and some general comments. Okay, Ana.
Now, my final question is an invitation. We hope to see you soon here in Brazil for our annual meeting, and also for the BMRS. And hope to see you soon next year, Aron, as soon as possible. And
I really hope
thank you very much for accepting our invitation. It's always a pleasure to listen to you. And then thank you for all the participants, and thank you for Juarez for hosting Aron. And also I'd like to thank my team that is on the backstage, Junior, Mari, and also Marcelo for the support. And see you next month for the next Cine webinar. So thank you, Aron, again.
Okay,
Thank you.
Okay.
Thanks.
Everybody stay safe. Bye-bye.
Bye.
It was nice.